If the source of light is a point, or can be considered a point, the light that comes from it will travel in all directions at the same time. Remember that light travels in a straight line. A single line of light coming from the point source is called a ray of light. Light travels in rays and beams. So what is exactly the difference between rays and beams? A beam is a collection of rays, and a ray is a path taken by a light. You see, several rays approximately parallel to one another form a beam of light. This is a so-called parallel beam. A spotlight is an example of a parallel beam. Next, we have divergent beam. Divergent beam is another type of beam of light. Divergent beam starts from a common point and then spreads out, just like what we can observe in a projector. Last, we have the convergent beam. This happens when all rays come from different directions and they all converge or meet at a common point. Example, inside the eye there is a retina, and all light that passes from the lens converge in retina. The meeting point of all the rays is called focus. When you are outside on a sunny day, you probably have noticed a dark image on the ground. This dark image is sometimes directly in front of you, beside you, or behind you, following you wherever you go. This is your shadow. A shadow is best described as the region behind an opaque object from which light is cut off. If the light falling on the hand comes from a point source, the hand cuts off all the rays that fall on it, and will produce a shadow, which is uniformly dark on the screen. This is the direct result of the propagation of light in straight lines. This dark area from which all the rays of light have been excluded is the umbra. Let's take a look at this example. If the light comes from a source larger than a point, like an incandescent bulb, the shadow on the screen will not be equally dark. This is because the light from the various parts of the larger source gets into the outermost portions and produces the penumbra, the portion of the shadow which is partly illuminated and lies between the region of utter darkness, umbra, and that of complete illumination. When light passes obliquely from one medium to another of different densities, or even within the same medium such as the Earth's atmosphere, it passes through different layers of varying densities. Its path is bent from a straight line at all places where the density changes. This phenomenon is a direct result of the fact that the speed of light slows down upon entering a denser medium, and that it speeds up when it passes into a medium that is less dense. Optical density is the property of a transparent substance which measures the speed of light through the substance. Light will therefore travel in a straight line only if the medium it travels through has uniform optical density. Based from the figure, when the ray of light enters a medium or water, where its speed is reduced, the ray bends towards the normal. While on the other hand, if light passes from one medium or water into a second medium into the air, where speed is greater, the ray bends away from normal. When wave fronts of light approach a prism obliquely, that part of each wave which enters the prism, which is a dense medium, slows down. That part of the wave which is still in the air continues with the same speed. This results in a change of the direction from segment EF to segment FG when coming out of the prism. The part of each wave which goes out into the air first speeds up, pulling the direction of the light rays towards the base. This bending of the light rays as they pass obliquely from one medium into another of different optical densities is called refraction. The speed of light changes in different substances. Light travels 3.0 times 10 raised to positive 8 meters per second in a vacuum. In water, it travels 2.25 times 10 raised to positive 8 meters per second, about three-fourths its speed in a vacuum. In ground glass, it slows down to 2.0 times 10 raised to positive 8 meters per second, or two-thirds the speed of light in a vacuum. The ratio of the speed of light in a vacuum to its speed in a medium is the index of refraction, or N, for that medium, and it remains the same whatever the angle of the incident ray upon the refracting surface. The index of refraction can be computed using the equation N is equal to speed of light in a vacuum all over speed of light in another material. In symbols, we have N is equal to C all over V. For example, find the index of refraction, or N, of ground glass using the data mentioned previously. We have given speed of light in a vacuum, which is equal to 3.0 times 10 raised to positive 8 meters per second. Another, speed of light in glass, which is equal to 2.0 times 10 raised to positive 8 meters per second. To solve for that, we have to use the formula N is equal to the speed of light in a vacuum all over speed of light in another material, which is equal to 3.0 times 10 raised to positive 8 meters per second divided by 2.0 times 10 raised to positive 8 meters per second. That will give us the answer 3 over 2. To simplify it, we will get 1.5. A pure substance has a definite and constant index of refraction. An unknown substance can therefore be identified by its index of refraction. The purity of products can be determined by their index of refraction with the aid of a refractometer. The quantitative relation between the angle of refraction, or theta sub r, and angle of incident, or theta sub I, was discovered by the Dutch physicist Wilbrod Snell in 1621 and is now known as Snell's law. It is written as n sub 1 sine theta sub I is equal to n sub 2 sine theta sub r. N sub 1 and n sub 2 are the respective indices of refraction of the material.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!